today, Monday? Wednesday we discussed what an infinite series was, right? What it meant for a series to converge. How we evaluate series. The vast majority of the time, we actually don't care what series evaluates out to. We just care that it doesn't converge. So the whole limit of the partial sums, don't really care about it. We just want to test that does a series converge or not. On this video, you're introduced to your second special series. Called P series. This is a P series. It'll converge only for P larger than 1. Diverges otherwise.
So, sorry, question. If P is 1, it
Diverges.
Okay.
Three tests were introduced. We have direct comparison. So we have two general terms, A sub n, B sub n, both are positive. We're also going to say that B sub n is larger for all n greater than equal to 1. Now, technically it just has to be after some starting point. And so it could be for all n greater than equal to 100. As long as it's true for every n at some point, or after some starting point, then you can use direct comparison. What it says if B sub n converges, then so does A sub n. If A sub n diverges, then so does B sub n.
What's the upside down A?
For all. Limit comparison. We look at the limit of a sub n over b sub n. Again, a sub n, b sub n have to be positive. If L is greater than 0, A sub n converges if and only if B sub n converges. I should actually specify L has to be greater than 0 and finite. If L equals 0, and B sub n converges, then so does A sub n.
Is that if and only if?
The first one's an if and only if.
The second one?
This one's an if then. Finally, if L is infinite and A sub n converges, and so does B sub n. Of the two comparison tests, I like limit comparison the most. It's easier in my opinion. Because we don't have to worry about finding a series that's larger or smaller. We just find a new series, try to get the limit to be finite greater than 0, and we're done. Because then the two series do the same thing. They can both converge or both diverge. Direct comparison, you have to kind of already know when the series converges or diverges. You have to have a hunch. So that tells you, do you want to find a smaller series that diverges or a larger series that converges? The third and final test for this evening is my least favorite. The integral test. So your term has to be continuous, positive, and decreasing for all n greater than or equal to 1. Again, just at some point beyond. Then the series converges if and only if the integral converges. So those are our 3 tests plus the special P series. Generally speaking, I use integral test only if I absolutely have to. All of these tests are valid only on what's called a positive series. A positive series is just a series in which every single term is non-negative. So a certain geometric series would be a positive series. Would there be what's called a negative series? Would you have a series in which every single term is negative?
If this starts from 0 or 1? Did they all have to start from 0? Or
What do you mean start from 0?
like on the bottom where it says n equals 1?
That doesn't matter. It's just right. So positive series doesn't matter where it starts as long as every single term is positive. So can you have a series in which every single term is negative?
I think technically if the thing starts negative, you can, but otherwise.
What do you mean starts negative? So again, I'm not talking about this term. I'm talking about the summed.
I don't think every single term can be negative because every other one will have to be positive. Can you only go up with n and not down?
And only goes up.
Okay. Yeah, I guess that would make every single term negative.
I argue it's still a positive series. subtracted out the -1, now I have a positive series. This is going to be multiplied by negative in the end. But that doesn't matter. Multiplying by a finite number doesn't change convergence or divergence. In fact, that series diverges. That's a harmonic series. So if every single term is negative, just factor out the negative and then treat it as a positive series. So we're going to test series for convergence, starting with this one. Let's first write that in summation notation.
It would be 1 over radical 2n plus 1.
And starting where?
0.
That works. That's not the form I'm going to use. We're going to start n at 1. And my reasoning for that will become apparent. That'll be 1 over the square root of 2n minus 1, right? Let's look at this limit. That's same thing as the limit of n over root 2n minus 1. What's that limit?
Those would still end up being the fitting into the pattern, right?
What? This?
Well, those on the board, those on the thing, but still after you, when you say,
Absolutely the same.
okay. So would it be approaching 0?
Oh, at this root n, no, they wouldn't be the same.
Okay.
But what's this limit? Making this tougher than it needs to be.
Is it 1?
One half.
And how do we get that?
I'm sorry, not one half. 1 over root 2. So two ways you can do it. Just look at the coefficients. This is n to the 1 half, n to the 1 half. It's 1 over root 2 coefficients.
Okay.
Or treat this as a single square root. Composite function theorem. It's the square root of the limit of n over 2n minus 1.
Okay.
What's the limit of n over 2n minus 1? What's that limit? It's 1 half, right?
Yeah.
Square root of 1 half. 1 over root 2. It's greater than 0. This series converges if and only if that series converges. What kind of series is that? It is not geometric. That's a P series. What's P? So does that converge or diverge? Diverges. Half is less than 1. Which means this series diverges by limit comparison. This is why, by the way, when we started at n equals 1. P series starts at n equals 1. So I wanted this to look like P series. So the series diverges by limit comparison. Well, let's look at this one. Do you agree with that statement? N cubed plus 2 is greater than or equal to n cubed
Yes.
for all n greater than or equal to 1. Obviously not true for negative n. But positive n it is. What happens to an inequality when you take the reciprocal?
It flips.
I'm only using direct comparison here to show you how it works. I would use limit comparison on this.
Where did we get those? I guess I see where we get 1 over n3 plus 2, but where do we get the n cubed from?
Because I want to compare it to 1 over n cubed.
Yeah, where did 1 over n cubed come from?
My head.
Okay.
Remember, I'm using a direct comparison. So I'm finding a series to compare it to.
Oh.
So I picked 1 over n cubed.
Oh, okay, so it could just be any one. Okay.
1 over n cubed is the easiest one to see. 1 over n squared would also work.
So these, we can just pick any other series. And
You have to be careful. For limit comparison, yes.
not really.
For a direct comparison, it depends on whether you want convergent or divergent. You need either a larger series or a smaller series, depending. I'm doing a smaller series. Because I think 1 over n cubed plus 2 is going to converge. What does that series do?
It's the limit is 0.
Okay, what does that tell you?
It converges?
No.
No, it diverges. Oh, wait a minute. That he converges if they converges.
Oh, this is my b sub n. This is my smaller series for direct comparison, or my larger series for direct comparison.
Okay.
So I want to say, what does this series do? There's a reason why I chose 1 over n cubed. What kind of series is that?
Oh, it's a P series. And 3 is greater than 1.
So what does the series do?
It converges.
So I found a larger series that converges, which means my smaller series has to converge.
So B sub n would have to be larger than A sub n.
Converges by direct comparison. So I could have used 1 over n squared. That also converges, right? That's a P series. However, that is also a true statement, is it not?
Yeah.
What does 1 over n do? So if I just remove the 3, what does that series do? That now diverges. That's the harmonic series.
Yeah.
Direct comparison test fails. All I found was a larger divergent series that says nothing of the smaller series. And so that's why I said you have to be careful with direct comparison. So if I would have used 1 over n, I would not have gotten an answer. But 1 over n cubed gave me an answer.
So for direct comparison, it should say B sub n converges, then A sub n converges if and only if, right?
Not an if and only if.
Oh, okay. So if that happens.
Right, so direct comparison says if your larger series converges, your smaller series has to converge.
But if it doesn't converge.
If your smaller series diverges, then your larger series has to diverge. Right, so that's why I said it's 2 different results, not 1.
Oh, okay. So if the larger series converges.
The smaller one has to converge.
And if the smaller one diverges.
The larger has to diverge.
The smaller one diverges.
If the smaller one converges, it doesn't say anything about the larger.
And then
If the larger diverges, it says nothing of the smaller.
Okay.
Right? The idea behind that is simple, right? 1 over n cubed in this case acts as an upper bound. Right?
Yeah.
Which means this sum would serve as an upper bound for this sum.
Okay.
Well, if my upper bounds converge into a value, then the series has to converge because the upper bound is converging. Right? Does that make sense?
Yeah. Yeah.
Right, but if it diverges, whatever, upper bounds diverge, whatever, it doesn't say anything about my smaller function. And the same idea is applied the other way. If you have a smaller series that acts as a lower bound, right? So if that diverges, your lower bound diverges, no way in hell your larger term is going to converge. Because your lower bound is divergent. But if the lower bound converges, it says nothing of the upper, of the larger function. It could converge or diverge.
Okay.
Right? That's the sense of the direct comparison test. So I would have used limit comparison on this. With 1 over n cubed. And gotten the same result. Okay, so now we look at this series. So 1 over n factorial. This is a case where limit comparison isn't going to be useful. Okay. There's no series I can think of that has a finite positive limit, and I know what that comparison series does. However, actually, I'm going to work with 1 over. Let's start with n factorial. N factorial, 1 times 2 times 3 times 4 up to times n, right? Well, this greater than or equal to one times 2 times 2 times 2 times 2 times 2, so on and so forth. Where there's n minus 1 2's, right? So basically, an n factorial from 3 on, replacing the 2. That would make this larger. That's just 2 to the n minus 1. So n factorial, I'm saying, is greater than or equal to 2 to the n minus 1 for all n greater than or equal to 1. They would be equal when n is 1 and n is 2. Right? Because that's these two terms which aren't being replaced. This would now be strictly greater than for n greater than for n3 or larger, right? But that's not what direct comparison test says. It has to be strictly larger. It just has to be or equal. There we have n factorial greater than or equal to 2 to the n minus 1. Take the reciprocal. So we have 1 over 2 to the n minus 1 is larger than 1 over n factorial. Greater than or equal to 1 over n factorial for all n greater than or equal to 1. So look at this series. Because this is the same as this. Isn't it? Instead of starting at 1, I'm going to start at 0. Same series. Right? What does that series do? First of all, is that a series you recognize? It isn't? You should recognize it.
Not the power series, right? Because the ends in the.
Well, we haven't studied power series yet.
I mean, P series.
No, so that's not a P series, I agree with that.
Right.
And that's why I said you should put them all on a separate sheet of paper so you don't have to flip through your notes. Look, just right there, one nice reference. What other type of series did we study? Studied it last time. Geometric! What's R?
Was it 1/2?
1/2. Isn't 1 over 2 to the n the same as 1/2 all raised to the n? Is that geometric converge or diverge?
Let's see. Is that R is 1/2? It's less than 1, so it converges.
So 1 over 2 to the n for n equals 0 to infinity is a convergent geometric series, which means this is a convergent geometric series. Right? So this is convergent geometric, this converges, but that's larger. So the series converges by direct comparison. Let's write this in summation notation. What is the general term? So we're going to have a numerator and denominator. We all agree? Let's look at the numerator first.
I think it would be n over parentheses n minus 1 and parentheses cubed.
And n starts where?
No. That would, that's saying that n starts at 3.
3? It wouldn't be starting at 3.
Yeah.
Because if n started at 3, what's your first term?
3 over 8.
What should the first term be?
2. So it starts at 2.
Check that.
Yeah,
2 over 1 cubed 2. That would work. Again, that's not the form I'm going to use. We want n to start at 1. Again, that does work. But for what I'm going to be doing, actually, you know what? That thought. Let's do it at 2.
okay.
And I'll see what happens. So let's look at this limit. So notice what I'm setting my b sub n to be, right? This is the a sub n. This is b sub n. So I'm setting b sub n to be 1 over n squared. Simplify that. What do you get? What fraction do you get? And don't worry about expanding anything. You don't have to worry about expanding out the n minus 1 cubed.
N over n squared.
Go here. Go here. How do you divide fractions?
Multiply the reciprocal.
You need to multiply by the reciprocal.
And then cube it over n minus 1.
What's that limit?
I think it's probably going to go to 0 or a coefficient. Is it an infinity?
Why?
Because it's not minus 1. Eliminating the difference. It's like
If you actually expand this out, your first term's an n cubed, right? N cubed over n cubed is 1. Remember, same degree, look at the coefficients. Look at the ratio of the coefficients. Which is why I chose 1 over n squared. I purposely chose 1 over n squared to get a limit of 1. The broadest idea of limit comparison, try to get a limit of 1. So you look at this term, you go, how does that term behave as n goes to infinity? Behave as n over n cubed, right? Which is 1 over n squared. There's my comparison. 1 over n squared. Well, that's greater than 0 and finite. So this series is going to do whatever this series does. So we have to look at that series. But there's a problem. N starts at 2. Which means what I'm looking at has to start at 2. What kind of series does this look like?
Looks like the one we. No, it actually looks like a P series.
Looks like a P series. Is it a P series?
No.
No. Why?
Because n equals 2. It's supposed to be 1.
But if we add or subtract a finite number of terms, it doesn't change whether the series converges or diverges. Keep in mind, I added 0, right? I added my n equals 1 term into the series to get a P series, but that n equals 1 term is 1. So I then immediately subtracted 1. So I didn't change the series at all in this case. This will converge if this converges, right? If you take a convergent series, add a term to it, in this case I'm adding -1, it still converges. If you take a divergent series and add a term to it, it still diverges. So now the question boils down to, what does this series do? Now here's a hint. Why did I want that to be n equals 1 instead of n equals 2? You said it already.
Yeah.
Why do I want that to be
So
n
do
equals 1?
you have P series?
That is now a p series, isn't it? What does this p series do? That converges, which means this whole thing converges, which means this converges. I'm going to use shorthand because this series converges. So what does this series do? Converges by limit comparison.
Yeah.
Oops. See that? For shits and giggles, let's say I gave you that series instead. What does that series do?
Does it also converge?
Why would it converge?
Would that still be a P series or no? The way it is.
Well, this itself was never a p series.
Okay.
Even when it started at 2, it wasn't a p series. It resembled one for large n, right? But itself wasn't a p series. So you think it still converges? Does anyone think it diverges? That series diverges. Why?
of it. I have it written down, but I don't quite remember what it does. Means looking at the divergence test.
What happens at n equals 1?
One. It's discontinuous.
The term doesn't exist.
Yeah.
Series diverges automatically. What if it was that instead?
It would diverge.
Why?
110 equals 4.
One of your terms doesn't exist. Right? If at any point you have a term that does not exist, the entire series has to diverge. It cannot converge. So if you notice that right off the bat, you're done. You can just say diverges because, in this case, when n equals 4, you get a non-existent term. So what about here? One over n to the n. So there are two paths we can go down here. Start with n to the n. Look at 1 over n to the n, and I go, well, that series, I could compare it to a p series. Or I could compare it to a geometric series. Either one's going to work. So I'm going to say n to the n, isn't that going to be larger than 2 to the n for n greater than or equal to 2? That means 1 over n to the n would be less than or equal to 1 over 2 to the n for all n greater than or equal to 2. Again, notice that n has to be 2 or larger. I do that. No idea. Shift the index. Two to the n plus 2 is 2 to the n times 2 squared, right? That's where the 1/4 is coming from. What does a series do?
Converges.
Why?
Because of the geometric series.
That is a convergent geometric series, which means this series converges by direct comparison. Was that our series?
No.
Our series starts at 1. So I said this is important. Right? Because this had to start at 2, this has to start at 2, and this had to start at 2. But since I know this converges, if I add something to this, it's going to converge, right?
Yeah.
So if I add 1, it would converge, right?
Yeah.
But 1, isn't that 1 over 1 to the 1?
Yeah.
That's the n equals 1 term. Does that mean that our series converges? Right? Because all I did was took the series I know converges and added some value to it.
If you didn't get the n equals 1 term, would it still converge?
What do you mean?
Like if let's say that the n equals 1 term didn't evaluate to 1.
Yeah.
It was
I just add whatever it would evaluate to. Let's say it evaluated to 8, I just add 8.
Okay.
Now I have the original series. Right? So you just want to add your n equals 1 term in. Or, if this started at 5, I'd add in my 1, 2, 3, and 4 terms
Okay.
to get back to the original. But it doesn't matter because I'm still adding in a finite value. So it would still converge.
So if something starts at a number other than 1 and converges, it's pretty much going to converge anyway. Okay.
Well, no, not necessarily.
Okay.
1 over n squared converges.
Okay.
But if I go to n equals 0, it now diverges. Because now you have 1 over 0. So you have to be careful. You have to add in finite values that exist.
Oh, so you have to make sure that none of them are
Right.
discontinuous.
Yes.
Okay.
Let's look here.
Does it automatically converge if it has a limit?
Define what you mean by it has a limit.
If for all the numbers you plug in, they all approach a particular number.
What number?
Well, in this case, it looks like it would be 2/3.
Well, if that limit is 2/3, then it would diverge by divergence test.
Actually, maybe.
Remember, divergence test says if the limit is not 0, then the series diverges.
Okay, actually, I don't think that's 2/3. Now that I think about it.
All right, so this is another case where direct comparison is going to be pretty difficult to do. But there's still another comparison. What should I compare this to?
N squared plus 1 over n cubed.
I don't know what that series does. So remember what I said earlier.
Maybe a B series.
Which one?
1 over n to 1.
Use 1 over n. How does that simplify now?
N cubed plus n over n cubed plus 1.
What's that limit?
1.
Finite greater than 0. What does that series do?
Diverge.
That diverges. So divergent P series, specifically it's the harmonic series, which diverges. So what does the original series do?
Diverge.
Has to diverge by limit comparison. See that? What do you want to do here?
Compare it to 1 over n.
How do they compare? Which one's larger?
1 over n.
What does 1 over n do?
Diverges.
Doesn't tell us anything. You found a larger divergent series, doesn't say anything about the original. What happens if I do this? What does 1 over log n do? No idea. Bummer. Our comparison's gonna work.
Oh, we have to do an integral then?
You don't have to.
Okay.
If you're really good with limits, you can use limit comparison. Oh, wait a minute. No, that's not going to work. Never mind. It will. No, that won't work. Never mind. I think if I use 1 over n plus 1, it'll work. I think that'll give me a limit of 1. Then I just have to go, what does 1 over n plus 1 do? And I go, well, that diverges by comparison. So you'd have to be clever and use a couple steps. Because I haven't shown off how it works yet, I am going to use an integral test. Oh, wait a minute. Ha-ha! There's a typo. If that was the question, this would be even easier. That straight up diverges. What's log of 1?
1? 0?
It's 0.
Oh, yeah.
That's not supposed to be a 1. That's supposed to be a 2. Now it's not so obvious. So look at this function f of x. Notice it's the exact same thing, I just replaced n with x. What does the integral test say? F has to be what?
Continuous, positive, and decreasing on from 1 to infinity.
Well, in this case, 2 to infinity.
Or 2 to infinity, yeah.
All right, the test says 1 to infinity, but it's wherever we're starting at.
Okay.
So I'm starting at 2 here, so I can just do 2 to infinity.
Okay.
Is that continuous? For x greater than or equal to 2?
Yeah.
Yeah. Is it positive?
Yes.
Is it decreasing?
Yes.
In this case, it's obvious that it's decreasing, right? Because your numerator is staying constant and your denominator is just getting larger. Because both x and log x are increasing functions. If it wasn't obvious, you have to do the first derivative test. Right, you have to take the derivative and show that the derivative is always negative on your interval. The conditions for integral tests are satisfied. So now we look at this integral. Ooh, it's been a while. How would you evaluate that integral?
We'd have to be by parts, and we need the table.
Before you even do that, before that, in a while. Been what, 2 months?
Yeah.
Oh dear, figured out how to integrate. That's not good. That's really not good. That's bad. It's kind of like the whole theme of Calc 2. It's called integral calculus.
Infinite integral.
It was the 7th meeting. Which was 12 meetings ago, plus the midterm, so it was 13 meetings ago. Yeah, so it was like 6 weeks. 6.5 weeks. Oh, it's been a while.
So we would have to put that integral at 2 at the top, and then what would it be?
2 at the top?
Yeah.
Or to be at the top?
Yeah, because I'm looking at this and it says limit.
You wouldn't move 2.
Okay.
But you're on the right page. This is improper.
Yeah.
Replace infinity with b and take the limit as b approaches infinity. I'm too lazy to write that out. So I'm going to do this. I think I mentioned it. Or I'm going to keep the infinity, and it's going to be an implied limit. This is u sub. Let u be natural log of x. What's the derivative of log x?
The derivative of log x is 1 over x.
I have 1 over x dx. What's the antiderivative of 1 over u?
Is it on the table?
Yeah, it's one of the basic forms. So you should remember from Calc 1.
Ln u plus c.
But u is natural log of x.
Yeah.
Now, I don't need the absolute values.
So we're going from 2.
Because log of x is positive
Right.
over 2 to infinity. So I can just drop the absolute values. I don't need it. Now remember, this is an implied limit. So what is the limit of the natural log of x as x approaches infinity? So what does natural log do?
Increase.
Specifically, does it increase to a specific value?
Nothing increases to infinity.
It would increase to infinity.
Yeah.
This is infinite. Then you play the same game. So if this is increasing to infinity, this is now the limit of log of x as x goes to infinity, which is infinite. This is infinite. It diverges. Right? So keep in mind that this isn't really natural log of infinity. I'm not evaluating at infinity, because infinity is a concept, right? It's not a number. It's implied to be a limit. This is just how we write it. So the integral diverges. So what does the series do?
Diverge.
Diverges by the integral test. Any questions so far? It's going to take a while to get used to this. To be completely honest, to get really comfortable with it, it's going to take longer than we have. I think we spend we spend 3 weeks. To get really comfortable with it, it's going to take a lot longer than 3 weeks. I've been doing this for decades. That's why I'm comfortable with it. It is a completely different way of thinking. The best thing you can do is just do a bunch of problems. You'll start to recognize patterns. When you do enough of them, you'll see with the limit comparisons what to compare it to, how I came up with those so quickly. You'll be able to just see, oh, I should compare it with this. You'll look at a series form like this one and immediately know, crap, I have to use integral test. You'll know when to use direct comparison. You'll know when to use limit comparison. And by the way, those are just 3 tests. We still have 3 more to go. Technically 4. One of them's not really that bad. It's called a subtest. So we want to use integral test on that series. And they're nice enough to actually set up the integral for you. What does that integral evaluate out to? And so you can either do it by hand or just plug it into a calculator. Uh-oh. Shouldn't take that long. Should be e to the negative 3 over 3. No, it should be. It is. I verified it. Right, antiderivative e to the negative 3n. Negative a third e to the negative 3n. Right? U sub. Well, limit of e to the negative 3n as n goes to infinity is 0. So you get minus, negative, positive, a third, e to the minus 3. Based on that, does the series converge?
No, diverge. No, wait. Not necessarily.
And so the improper integral converged. So what does the series do?
Converge.
Converges. Okay, so they want us to use integral test again. So first, would the integral test apply?
Can n be like decimals and things too? And fractions? Or they can only
No, technically no.
Okay.
And is only an integer.
Okay.
But it starts at 2, so is it continuous? So n greater than or equal to 2.
Like what, 2 to the n?
And so would it be continuous for n greater than or equal to 2? Yes.
Yes.
Right, it's not undefined.
Right.
Is it positive? Yes.
Yeah.
It'll always be positive. Is it decreasing?
Yes.
Yes, it will be decreasing. So integral test does apply. So we have to take the integral. So the integral exists. That integral converges. So the series would converge, right? By integral test.
How did we know that that number converged?
What number?
The answer that you got for
Oops.
the integral.
Well, that answer exists, right? It's a finite value,
Yeah.
so it converges.
Oh, so if you just get a number, it automatically converges.
Right, so this is saying that this integral converges to that value.
Okay.
So a couple comments. Boop. You can now work on assignment 18. Remember that that grouping is coming due. That's due April 17th, which is next Wednesday. You have 2 assignments due on the 10th. Also, your 3rd exam is handed out to Wednesday and will be due on the 17th. Wow, we're already up to exam 3. That means there's only one more quiz and the final exam after that in terms of assessments. We are reaching the end. Have a great evening. See you Wednesday.